Hey there, and welcome to another deep dive. Today, we're tackling a cosmic mystery that's been puzzling scientists for decades. Dark matter and dark energy. You ready to unravel the invisible forces shaping our universe?
Absolutely. These are some of the most exciting and mind-bending concepts in modern astrophysics.
Our guide for this deep dive is a YouTube video from the History of the Universe channel. It's called Where Did Dark Matter and Dark Energy Come From? It's a great place to start because it really dives into the discoveries, the evidence, and what we still don't know about these elusive forces that make up the vast majority of our universe.
It really lays the foundation for understanding how scientists first came to realize that there was something more out there than meets the eye.
And speaking of seeing the unseen, let's rewind the clock back to the 1930s. Let's meet Fritz Zwicky, a pioneering astronomer who was studying the Coma Cluster, a massive collection of galaxies about 300 million light years away.
Zwicky was trying to figure out the cluster's mass. By observing the speeds of the galaxies within it, the faster they moved, the more gravity was needed to hold them together, and therefore, the more massive the cluster had to be. Simple enough, right?
Seems logical to me. So what did he find?
Well, his calculations showed that the galaxies were moving way too fast for the amount of matter we could actually see. It was as if there was some invisible stuff providing extra gravity, something we couldn't detect with telescopes. He called this mysterious substance Dunkelmaterie, which translates to dark matter.
So right from the start, there was evidence suggesting the universe contained more than meets the eye. What's fascinating is that Zwicky also predicted gravitational lensing, the idea that massive objects, including this unseen dark matter, could warp the fabric of space-time and bend light, like a cosmic magnifying glass.
He was truly ahead of his time in many ways, even predicting that galaxies and galaxy clusters could be used to observe this lensing. Decades later, his prediction about gravitational lensing was confirmed.
Okay, let's unpack this gravitational lensing idea a bit more. How does a massive object bend light? Isn't light supposed to travel in straight lines?
That's where Einstein's theory of general relativity comes in. It tells us that gravity isn't just a force, but a curvature of space-time itself. So when light passes by a massive object, its path gets bent. By that warped space-time, it's like rolling a marble across a trampoline that has a bowling ball in the middle. The marble's path curves because the bowling ball has distorted the trampoline surface.
Ah, that makes sense. So are there actual observations that prove this bending of light?
Absolutely. In 1979, astronomers discovered what appeared to be a double quasar, two incredibly bright and distant objects that seemed to be right next to each other. They named it Q0957 plus 561.
Two quasars in the same spot? That seems unlikely.
It was. Further investigation revealed that it wasn't two separate quasars, but rather two images of the same quasar. A massive galaxy between us and the quasar was acting as a gravitational lens, bending the quasar's light and creating those two separate images. Wow, that's a pretty convincing piece of evidence for both general relativity and the idea of a lot of unseen matter in the universe.
It was a major breakthrough. And since then, astronomers have observed gravitational lensing in thousands of other cases. By studying how much the light is bent, they can essentially weigh those galaxies and clusters. And it consistently shows there's way more mass present than what we see in stars and gas.
And that missing mass is, you guessed it, dark matter. It's like an invisible scaffolding holding the universe together.
That's a great analogy. Zwicky's work was groundbreaking, but it would take another pioneering astronomer to really bring dark matter into the spotlight.
Let's hear it. Who is this new champion of the dark side of the universe?
In the 1970s, Vera Rubin was studying spiral galaxies, like our own Milky Way. She focused on how fast stars orbited the galactic center. The expectation was that stars farther from the center, where gravity is weaker, would move slower, just like planets in our solar system.
That makes intuitive sense. So what did she find?
Her observations showed something truly surprising. The stars on the outer edges of these galaxies were moving just as fast as the stars closer in.
Whoa, that's not what you expect. How could stars way out there be zipping around at such high speeds?
The only way to explain this was the presence of a lot of unseen matter, providing extra gravitational pull. It further cemented the idea that there was this invisible halo of dark matter surrounding galaxies.
Like an invisible hand guiding the cosmic dance.
Exactly. And just like Zwicky, Rubin faced her own share of challenges. As a woman in a field dominated by men, for example, she was initially denied access to observe at the Palomar Observatory because there weren't any women's restrooms. But her perseverance and groundbreaking discoveries were instrumental in solidifying the case for dark matter.
She was a true trailblazer. It's amazing how she didn't let those obstacles stop her from making such a profound impact on our understanding of the universe.
Absolutely. Her work was essential in establishing dark matter as a major component of the cosmos. But now, let's zoom out and consider the universe's large-scale structure, because that's where the influence of dark matter becomes even more apparent. We're talking about clusters, filaments, and voids, this intricate cosmic web that stretches across billions of light years.
I love the evocative names they give to these immense cosmic structures. The Great Wall, the Stickman, and Laniakea, which is our home supercluster. It really captures the scale and mystery of it all.
It does. Early galaxy surveys like the CFA Redshift survey started mapping the positions of galaxies and revealed this incredible, almost sponge-like structure, it turns out. Dark matter played a key role in sculpting this cosmic web.
Okay, let's unpack this. How does dark matter connect to the large-scale structure?
Imagine the early universe as a mostly smooth soup of hydrogen, helium, and dark matter. Over time, gravity, fueled by those tiny initial density fluctuations, caused matter to clump together.
Right, and because dark matter doesn't interact with light, it wouldn't have been hindered by the heat and radiation that would have slowed down regular matter.
Exactly. Dark matter would have started clumping together much earlier, creating gravitational wells. That pulled in the regular matter, setting the stage for the formation of galaxies and the intricate patterns we see in the cosmic web.
So dark matter is essentially the architect of the universe, providing the blueprint for everything we see today.
That's a great way to put it, to really visualize this. Astronomers use supercomputers to create simulations of the universe's evolution. These simulations vividly show how, without dark matter, galaxies wouldn't have formed nearly as quickly, or in the patterns we observe.
It's incredible that we can actually see these virtual universes evolve on a screen and witness the role of dark matter in shaping the cosmos. But this brings us to the million-dollar question. What is dark matter actually made of?
The mystery within the mystery. And the short answer is, we don't know for sure, but we can rule out some possibilities.
Let's play cosmic detective then. What can we eliminate from our list of suspects?
Well, we know it's definitely not regular atoms, because we'd be able to detect them with our telescopes. It doesn't interact with light in the same way that ordinary matter does.
Okay, so atoms are out. What about black holes? They're dark and massive. Could they be the culprit?
Black holes were definitely a strong contender for a while. However, astronomers have been searching for signs of black holes, acting as gravitational lenses, and they just haven't found enough to account for all the dark matter out there.
So black holes are off the hook, at least for the most part. What about neutrinos? Those tiny, almost ghostly particles that barely interact with anything. Could they be dark matter?
Neutrinos were a promising candidate for a time because they do fit the bill of being invisible and interacting very weakly with matter. But it turns out they're just too light and move too fast to clump together enough to form the large-scale structures we observe.
So if it's not atoms, black holes, or neutrinos, what are we left with? Where do we even begin to look for something that's essentially invisible?
This is where we enter the fascinating world of particle physics and the Standard Model, our best current description of the fundamental building blocks of matter and the forces that govern them. But there's a catch.
I have a feeling this is where things get really interesting.
You got it, the Standard Model. While incredibly successful in explaining many phenomena, has some significant gaps. It doesn't fully account for gravity, and it doesn't include a particle that could explain dark matter.
So it's like we're missing a piece of the cosmic puzzle. How are physicists trying to fill in this gap?
They're exploring extensions to the Standard Model, searching for new particles. That could be the elusive dark matter. And there are some intriguing theoretical candidates out there.
Okay, I'm all ears. Tell me about these potential dark matter particles.
One exciting possibility is the axion. It's a hypothetical particle that interacts incredibly weakly with matter. The funny thing is, it was named after a laundry detergent.
Laundry detergent.
Yeah.
I love it when serious science gets a dose of everyday humor.
It's true. Another intriguing idea is supersymmetry, which predicts that every known particle has a shadow partner particle. Imagine it like this. For every particle we know and love, like an electron or a quark, there's a supersymmetric twin lurking in a hidden dimension.
It's like a whole secret world of particles mirroring our own.
Exactly. And some of these supersymmetric particles could potentially have the right properties to be dark matter.
So it's like there's a whole cosmic shadow play going on. with dark matter interacting with our world in subtle, hidden ways.
That's a great way to put it. And there are even more candidates out there. Sterile neutrinos, WIMPs, weakly interacting massive particles, and many others. The search for dark matter's true identity is one of the most active and exciting areas of research in physics.
It's like a giant cosmic detective story, with physicists scouring the universe for clues to the true nature of dark matter.
It is, and just when you thought it couldn't get any more mysterious, the universe threw us another curveball in the late 1990s, the discovery of dark energy.
Dark energy. Okay. Now I'm really intrigued. We've explored the mysteries of dark matter, but now it seems we're venturing even deeper into the unknown. What exactly is dark energy, and how did it come into the picture? So we've been on this deep dive into dark matter, but the universe had another surprise in store for us, something even more mysterious and pervasive. Dark energy. It sounds like a cosmic plot twist.
It really was a paradigm shift in our understanding of the cosmos. In the late 1990s, astronomers were studying distant supernova, the incredibly bright explosions of massive stars. They were using these supernova as standard candles to measure the expansion rate of the universe.
And they were expecting the expansion to be slowing down over time, due to gravity, right? Makes sense to me.
Exactly. It was the logical assumption. All the matter in the universe should be pulling on itself, putting the brakes on the expansion. But that's not what they found. Instead, their observations showed that the expansion of the universe was actually accelerating.
Wait, accelerating. So instead of slowing down, the expansion is actually speeding up. That seems counterintuitive.
It was a shocking discovery. It implied that some unknown force was counteracting gravity, pushing everything apart. This mysterious force became known as dark energy.
So we've got dark matter holding things together, and now dark energy pushing everything apart. Sounds like a cosmic tug-of-war.
It's a fascinating interplay of forces on a grand scale. And here's the kicker. Dark energy isn't just a minor player in the cosmic drama. Current estimates suggest that it makes up roughly 70% of the universe's total energy density. Dark matter accounts for about 25%. And all the stuff we can see, stars, galaxies, planets, you and me, only makes up a measly 5%.
Whoa, so we're basically living in a universe dominated by things we can't even see or comprehend. It makes you wonder, what else might be out there? Lurking in the shadows, this unexpected discovery of dark energy really throws a wrench into our understanding of the universe's evolution and fate.
You're absolutely right. The discovery of dark energy forced scientists to reconsider some old ideas, including one that Einstein himself had famously dismissed, the cosmological constant.
Okay, I'm intrigued. What's the story behind Einstein's cosmological constant, and how does it connect to dark energy?
Back when Einstein was developing his theory of general relativity, he believed, like many at the time, that the universe was static, neither expanding nor contracting. But his equations kept suggesting otherwise.
So what did he do? Did he try to change the equation?
He added a term to his equations, a fudge factor, if you will, called the cosmological constant. This term acted like a repulsive force, counteracting gravity and allowing for a static universe.
So it was a theoretical tweak to make the math fit his preconceived notion of the universe.
Exactly. But then, Edwin Hubble's observations came along and definitively showed that the universe was indeed expanding. Einstein, realizing his error, famously called the cosmological constant his biggest blunder and abandoned the idea.
But wait, didn't we just say that the universe's expansion is accelerating? That sounds an awful lot like his discarded cosmological constant.
It does, doesn't it? The properties of dark energy seem to match Einstein's cosmological constant remarkably well. It's almost as if he accidentally predicted this mysterious force decades before we had any observational evidence for it.
Talk about an epic plot twist. So if dark energy is like this repulsive force, what does that mean for the future of the universe? Are we all just going to drift further and further apart into cosmic oblivion?
That is the most likely scenario, at least based on our current understanding. As the universe continues to expand at an accelerated rate, galaxies will be pushed farther and farther apart, making them harder to see. The universe could become a very lonely and dark place.
That's a pretty bleak picture. It makes you appreciate the preciousness of the time we have here in our little corner of the cosmos. But before we spiral into existential despair, let's explore some of the possible explanations for what dark energy actually is.
All right, let's dive back into the theoretical landscape. One of the leading contenders is the energy of the quantum vacuum. Have you ever heard of virtual particles?
I've heard the term, but to be honest, it's always sounded a bit like science fiction to me. Can you give me the rundown?
In the strange world of quantum mechanics, even seemingly empty space is teeming with activity. Virtual particles are pairs of particles and antiparticles that constantly pop in and out of existence, borrowing energy from the vacuum and then disappearing almost as quickly as they appeared.
So even nothingness has energy. That's mind-boggling.
It really challenges our everyday intuitions about reality. Some physicists believe that the energy associated with these virtual particles could be contributing to dark energy.
So that's where that massive discrepancy in the calculated energy of the vacuum comes in.
Right.
The one we mentioned earlier, the factor of 10 to the power of 120.
Exactly. When physicists try to calculate the energy density of the quantum vacuum, based on what we know about particle physics, the number they get is vastly larger than the observed value of dark energy. It's one of the biggest head-scratchers in physics.
So while the quantum vacuum is a fascinating concept, it seems like we're missing something big. When it comes to explaining dark energy, what are some of the other ideas that physicists are exploring?
Well, some have proposed that dark energy could be something called quintessence, a dynamic field that permeates all of space and changes over time.
So unlike the cosmological constant, which is, well, constant, this quintessence field could evolve and maybe even interact with matter. How would we even test that?
Precisely. The idea is that quintessence wouldn't be a static force, like the cosmological constant. It could change over the history of the universe, which might explain why dark energy's effects seem to have become dominant only relatively recently. Testing this idea would involve looking for subtle variations in dark energy strength over cosmic time.
Because like dark energy might not be a constant background hum, but more of a dynamic and evolving force. That's a pretty radical concept. And are there any other explanations on the table?
Some physicists have even proposed that dark energy and dark matter might be connected somehow. It's a long shot, but intriguing nonetheless. Maybe the two sides of the same coin, arising from some deeper, unknown physics.
Now we're really getting into the realm of speculation, but that's part of what makes cosmology so exciting.
Right.
Pushing the boundaries of what we know and venturing into the unknown.
Absolutely. And it's not just about coming up with wild theories. It's about finding ways to test those theories. We need observations, experiments, and data to guide us.
Speaking of testing theories, we talked earlier about the ongoing hunt for dark matter particles, like axions, and those elusive supersymmetric particles. What are some of the ways scientists are trying to trap these cosmic phantoms?
One approach is to build incredibly sensitive detectors, deep underground, shielded from the constant barrage of cosmic rays and other background radiation. These detectors are essentially waiting for a dark matter particle to collide with an atom in the detector material, producing a tiny flash of light or a release of energy. That can be measured.
So it's like setting a trap in the darkest depths of the Earth and hoping a dark matter particle wanders in. Have any of these experiments found anything?
There have been some tantalizing hints and signals over the years, but nothing conclusive yet. The search continues. Each new generation of detectors is more sensitive and sophisticated than the last.
It's a testament to human ingenuity, this quest to find something. That interacts so weakly with our world. But if those particles are so elusive, how can we even be sure they're out there? Is there any other way to look for them?
Another approach focuses on the idea that some dark matter particles might annihilate when they collide with each other, releasing energy in the process.
Annihilate, what does that mean in the context of particles?
It means that when two dark matter particles collide, they can convert their mass into energy, often in the form of gamma rays, which are a very high-energy form of light.
So astronomers are searching for these telltale gamma rays, hoping they'll lead us to regions where dark matter is concentrated?
Exactly. They're looking at places like the center of our galaxy, where dark matter density is thought to be very high, and some observations have shown an excess of gamma rays coming from that region.
So, more clues to follow. But have there also been observations that could be explained without resorting to dark matter at all? Something about modified gravity.
Yes, that's right. Some physicists believe that our current understanding of gravity, as described by Einstein's theory of general relativity, might need some tweaking, especially when we're dealing with the vast scales of the universe.
So instead of invoking these mysterious dark matter and dark energy entities, maybe gravity just works differently than we think. On those scales, that seems like a pretty radical departure from our current understanding.
It is. These modified gravity theories attempt to explain observations that we typically attribute to dark matter and dark energy by adjusting the laws of gravity. Some of these theories have had some success in explaining things like the rotation curves of galaxies, which we typically explain with dark matter halos.
But you said earlier that none of these theories have been able to explain everything.
What are some of the biggest hurdles these modified gravity theories face?
That's the crux of the issue. While they might explain some observations well, they often struggle to account for others, like the cosmic microwave background radiation or the formation of large-scale structures. They haven't been able to provide a complete and consistent alternative to the standard cosmological model, which includes dark matter and dark energy.
So for now, dark matter and dark energy remain the leading explanations. But it's fascinating to think that there might be other ways to interpret the data. It really highlights how science is a process of constant exploration and questioning. What might seem like a settled issue one day could be overturned by new discoveries or a different perspective.
Exactly. We should always be open to new ideas and challenges to our current understanding. It's what drives scientific progress.
Okay, so we've covered a lot of ground. We've talked about the evidence for both dark matter and dark energy, explored some of the leading theories about what they might be, and even touched on the possibility of modifying our understanding of gravity. I have to admit, my mind is swirling with all this new information.
It's a lot to take in, but it's also incredibly exciting to think about. All the unanswered questions and the potential for future discoveries.
Before we wrap up this part of our deep dive, I'd love to leave our listeners with something to ponder. Imagine for a moment that we could somehow communicate with a civilization from another galaxy. What questions would you ask them about their understanding of dark matter and dark energy?
That's a great question. I'd be curious to know if they see the same evidence for dark matter and dark energy that we do. Have they discovered the true nature of these phenomena? Have they perhaps detected dark matter particles? Or do they have a completely different explanation for what we observe? Maybe they've come up with the theory of gravity. That elegantly explains it all, without resorting to dark matter and dark energy.
I wonder if their observations of the universe, their cosmological models, and their theories are similar to ours, or if they have a completely different perspective. It would be fascinating to compare notes and see how their insights might challenge or complement our own.
It's a humbling thought, isn't it? To realize that our view of the universe might just be one perspective among many.
It really puts things in perspective and reminds us that we're still at the early stages of exploring the cosmos and unraveling its deepest mysteries. It really is humbling to think about all the different perspectives out there, all trying to make sense of this vast and mysterious universe. And it makes that question we pose to our listeners even more intriguing. What if we could actually see dark matter and dark energy? How would it change our view of the cosmos?
It's a question that sparks the imagination. Imagine looking up at the night sky and seeing not just stars and galaxies, but also the intricate web of dark matter. We might see halos enveloping galaxies, filaments stretching across billions of light years, a cosmic tapestry woven with invisible threads.
It would be like seeing the universe's hidden architecture, the scaffolding upon which everything else is built. And what about dark energy? Would we perceive it as some kind of cosmic fog, pushing everything apart? Or maybe something even stranger?
It's hard to say for sure, because we're dealing with concepts that are so fundamentally different from anything we experience in our everyday lives. But if we could directly perceive dark energy, it would likely revolutionize our understanding of space and time. After all, it's the dominant force shaping the evolution of the universe, on the grandest scales.
Maybe it would appear as a subtle distortion of space-time, or variations in the brightness of distant objects. Who knows? It's a bit mind-boggling to contemplate.
It really stretches the limits of our imagination. But that's the beauty of exploring these fundamental mysteries. We're constantly pushing the boundaries of what we thought was possible.
And who knows? Maybe someday our current theories about dark matter and dark energy will seem as quaint and outdated as the idea of a geocentric universe.
That's the nature of scientific progress. New observations and theoretical breakthroughs can lead to radical shifts in our understanding. What was once considered revolutionary can become textbook knowledge, paving the way for even more profound and mind-bending discoveries.
I think that's a perfect note to end on. This deep dive has been an incredible journey, exploring the invisible forces shaping our universe. From the first hints of dark matter to the mind-boggling implications of dark energy.
We've covered a lot of ground, from the historical discoveries to the cutting-edge research that's pushing the boundaries of physics and cosmology.
And we've only just scratched the surface. There's so much more to learn, so many more questions waiting to be answered.
To our listeners, we encourage you to continue your own explorations. Delve into the fascinating world of dark matter and dark energy, read books, watch documentaries, follow the latest research, and most importantly, never stop asking questions.
Because Every question is a stepping stone on the path to understanding, a chance to expand our knowledge and appreciation for the vast and mysterious universe we call home.
So keep looking up at the stars, keep wondering, keep exploring, because even in the darkest corners of the universe, there's always something extraordinary waiting to be discovered.
And on that note, we'll see you next time for another deep dive.